I'm Dmitry, this is Thorsten. So maybe, yeah, we'll start by talking about ourselves, even though we got this nice introduction from Hugo. So I'm a PhD student in Berlin, at TU Berlin, at the Security and Telecommunications Research Group. I mostly do IC security, so thinking of, crazy new ways to hack ICs, as opposed to the classical ways to hack ICs, which is kind of the talk that you'll see from Olivier tomorrow. So if you ever want to come up and talk to me about chips and stuff like that, go for it. That's my favorite, one of my favorite topics to talk about.
Yeah, I am Thorsten. I'm also from Berlin, and I don't work together with Dmitry at the university, but I work at Mod0, which is a Swiss-based company, but I anyway live in Berlin. So my background is more like doing software security stuff and doing and researching hardware since a couple of years now, but I'm basically from the software side of IT. So that's what we do.
You're recovering though.
Yeah. However, this talk is basically about hacking hardware, and we just built some tools which will ease the process of hacking hardware. So we a couple of times we just figured out that the de facto standard tools are not sufficient for analysis. So we just tried to build a new way to implement your own tools in logic. So that's basically what we have done with the Datenkrake. It's an FPGA and an ARM, and you can basically implement your own hardware hacking tool in logic. So I mean,
we'll get into the details.
Yeah.
Don't tell them everything right now. Okay, but the motivation is, we want to avoid warranties. We want to open up, embedded devices, connect directly to them. And the point is, this first part of our talk is to show you why this is hard to do with current tools. So
let's just introduce some tools that are useful for analyzing embedded devices. So I mean, the first thing you're doing when opening a device or trying to analyze some devices, you're most likely using one of these read-only tools for sniffing on the bus to analyze the behavior of your target embedded device. And so there are a couple of drawbacks with using these devices. For example, you can only read data. So I mean, you cannot just inject or, you can only read data, but they're pretty,
Yeah, okay. No, but so the point is if you have an oscilloscope, you can think of it as a read-only device. The only thing that you can do with an oscilloscope is it has basically an A to D inside in some way with some sort of resolution. So it translates the voltages that it sees to digital data, which you can save in your memory that's within this oscilloscope, but there's absolutely no way to have these devices speak to the outside world. I mean, at least not for the kind of speaking that we want them to do. So on the right is what I have at the university, and for those who have never seen this is a nice LaCroix WavePro 7 ZI with 3.5 gigahertz of analog bandwidth and 128 megapoints of sample memory per channel. And this thing costs 120,000 euros. So this might not be what you want to buy if you're getting into hardware. It might be out of your price range. But it's an awesome tool. And actually, the university got it for 55, because the CEO of LaCroix Europe called me personally and said, we're giving you the best deal LaCroix has ever given anyone in Europe. So, but even 55,000 is still expensive for a tool like this. And like we said, it only does half of the things that we wanted to do. So there's also cheaper alternatives, like the picoscope. The picoscope, we have some here. If you take the workshop, we'll be playing around with picoscopes in another room. There are these nice USB attached oscilloscopes, but the point is they're lower end, and again, even these devices, they're still cheap, but they're still read-only. So now we get into microcontrollers, and there's tons of microcontroller projects. So there's the Arduino, which everyone knows. It's very cheap. I mean, I use these also if I need to put something together really fast. So the Arduino is quite nice because not only does it, it also exposes the pins. It's very nice to connect to it. There's also the GoodFET, which I hear neighbor Travis is around here, you can go, yell at him. He'll give you some PCBs so you can solder it together yourself. But the best example is maybe the bus parts. So maybe.
Yeah, all of these projects are quite good for doing some analysis on embedded devices when you're going to snip buses, for example. The advantage of these projects is that there are currently a lot of tools available for this microcontroller project. So if you want to analyze some specific protocol, you will most likely find whatever you need already in software. So it's not only the hardware that is necessary to do analysis on embedded devices, it's also the entire tool chain, the software that runs on the device and on your computer, and that's why GoodFET and BusPart is a really good example, because there's already a lot of software available for doing all the analysis and sniffing stuff.
But so, the other thing is, which we'll be getting into, nowadays, I think most people, Alex just did a talk, so I'm talking about some ARM stuff as well. We're mentioning some of the ARM stuff. And so nowadays, if you ask us and you want to do a new project and you want to get something up, running up and running quickly, and you want it to be portable, there's no reason why you should use these, quote unquote proprietary microcontrollers. It would be much nicer to use ARM, just use the GCC toolchain that you get with ARM, and everyone, I bet half the people in this room already have it installed on their computer and are good to go. So that's kind of the minus point about these projects. But nevertheless, they're cheap, so they don't cost much at all. So the GoodFET being the cheapest because Travis gives you the board and you have to buy the parts.
Install it by yourself.
Yeah, and solder it, but everyone gets to learn how to solder then. Okay, but that's not what we want to. We want to talk about feldprogrammierbare Gata-Anordnung. Okay, so we'll let Hugo try to pronounce that one during the break too. So what's the advantage of these tools? The advantage of these tools is you basically can write the microprocessor yourself. You can write anything into an FPGA. You can write a full ARM. You can write an AVR if you wanted to and use AVR GCC. You can write your own basically chip that does whatever you want it to do. And that means whatever you want it to do in real time. So you don't have the software overhead of reading in the pins, writing to memory, etc. You can do this all in a single clock cycle because you write the hardware to do have this one purpose, and you make it as big or as small to be able to execute things in a single clock cycle. But the point is, if you were to go out today and buy a board like this, which is the main Xilinx board out right now, although I don't know if the 7 series is out yet. It definitely was the highest end board they have had out a couple of months ago, or at least a year ago. So this is a Vertex 6 development board. And the point is, if you were to go out and buy this is not useful for doing any kind of embedded hacking. And so why is that? The main so it has some nice things, like it has these dip switches in the corner. It also has some nice push buttons, which are also useful for if you're designing something very simple. And it even has, this memory card connector. So these are useful things. But look at all of the other stuff that you get on this board, which is not that useful. Which, for example, this fiber port, because clearly anybody who's starting, off in FPGAs wants to attach to some, 10 gigabit link and implement their own 10 gigabit controller. And so you also see these BNC connectors, which are great if you have an oscilloscope like I showed you on the previous slide. So not very useful in practice. And then there's also, it also just has DDR3 on it. I mean, it just has a SODIMM, so I mean, why not, right? I mean, but do you really need this? And the answer is probably no. And it also has PCI Express, which you also, let's assume you're trying to sniff something in your car. So now you have this board on the floor of your car with a PCI Express connector on it. That seems a little unnecessary. But so what you also get is my least favorite part, so to say, which is these obnoxious headers. So at the university, we actually had, I keep telling everyone this story that I remember I was talking to one of the teaching assistants, and so they have one of these boards, and he proudly told me, we had a bachelor's student sit there and try to etch and solder boards to just have one of these connectors on there, and he spent 2 weeks, but he got it, he got it running, just at home, just soldering, using just regular etchants and using a UV box. He actually got it up and running. So I mean, good for him, but I mean, this is not what most of us want to spend our time doing. So these connectors are horrible. And beyond that, this thing costs a lot of money too. Okay? But there's better boards, and we can take a look at them very briefly. And we also, the point is, you want an easy way to basically take, your building blocks, your Legos, and construct something completely custom. So there are nicer boards. There's for example, the Sasebo. I couldn't think of the word. The Sasebo. It's a board from. It's basically a side channel analysis board. So a lot of university labs who do side channel analysis may have these boards. And so this, at the very least, has headers that we can connect to, which are nice. I mean, we can now, it now makes it easier to design something custom using a board like this, but it's still expensive. The other ones are actually, we would recommend more. So for example, this Mojo is a Kickstarter project which just got funded, and I got my board recently. It's not a bad board. It has female headers as you have on the Arduino. But again, these boards alone are not perfect. So there was an awesome thing that Bunny had on his blog right around Christmas. I guess it was like 2 years ago. But I saw it, and I was very happy about it because it's the truth. If you ever design anything, break out all your GPIO, or everyone else will hate you for it. And that's why I don't understand it. It's not. They don't even understand. The designers of these FPGAs, it's as if they, ignore that people will be doing something beyond, what they designed this board for. And it's supposed to be a development board, right? So you're supposed to get this board. It's supposed to be easy to connect it to other things and do something completely custom, but it isn't. So there's, the future is here. And trigger warning for people who are afraid of rainbows.
We built Die Datenkrake.
So this was actually at we were at PH Days, and we had there was a crazy, gigantic, super bright rainbow outside, and I said, Thorsten, I'll be damned if we don't go make a picture with the rainbow shooting out of the Datenkrake, and so we did. Yeah. So what's the DDK?
Yeah. So in short, we call it DDK. So maybe it's also easier for Hugo to.
Oh yeah, so actually we should maybe mention what Datenkrake means. We forgot. Okay, so Datenkrake is a German word for companies with questionable privacy policies. So what it means is data octopus. So these are companies that are crawling all over your data and scooping it in and and feeding it off to Prism. Okay? So yeah, it's completely open source hardware and software. So yeah,
we learned our lesson from the mistakes of all the other boards. So we tried to combine all the best from the microcontroller-based projects and also from all these FPGA developer boards that are not that easy to use for hacking hardware and embedded devices. So yeah, we decided to build a board that you can easily attach to your targets, and you can also just use all the GPIO, the pin headers, to attach the Datenkrake to your breadboard to do other stuff. So, and yeah.
But we'll get into the details in a second.
Yeah, exactly.
But so, yeah, again, it's user-friendly, so that we did things which other boards don't do, like test pads. So maybe, I mean, we had an awesome use of test pads recently when we were, because for people who don't know, if you make 150 of these and you want to give them out at a conference, you should test all of them, to make sure that something didn't go seriously bad during manufacturing. So Thorsten and I came a couple of days before our training, and we were testing them. And we had this interesting issue where one of the Datenkrake, it wouldn't want to be programmed no matter what. And we were having all these crazy issues, and we were sitting there for an hour. And finally, I said, you know what, Thorsten, this isn't making any sense to me. I'm getting the multimeter, and I'm measuring the voltages, which is, by the way, for those who don't do electrical engineering, the first commandment of debugging electronics is thou shalt measure voltages. So we got out the multimeter, we started measuring the voltages on the test pads, and so basically it turned out that Thorsten's USB hub was providing 3.7 volts instead of 5. So good choice in a USB hub.
Oh, it was directly attached to the Mac.
Was it? No, it wasn't direct. It was good. Okay, good choice, and you shouldn't get a Mac next time. Okay, but anyway, the point is just highlighted too, on a lot of these boards, what you won't get is access directly to the pins. So if you want to do something completely custom with this board, if you say, you guys just put all this engineering effort into terminating things and making it so you probably won't blow your computer and all of this other stuff, I want to do something crazy, you can disable everything and have direct access to the I/O and just make plop a board down on top of it to do any sort of termination or whatnot. So you can basically, the other thing is you can bridge directly to the outside world and use the connectors that we have there as well.
So we decided to choose one of these NXP LPC processors for interfacing to the user or the hacker and the FPGA. So there are no special reasons why we choose this one, but I mean I know this LPC the best, so we just choose this one. It runs with 100 megahertz. It has 256 kilobyte of flash ROM and 64 kilobyte of RAM. So it is definitely enough to implement some analyzers and software. So you can easily just take whatever data is passed by the FPGA and do the analysis right within the ARM.
Yep.
Core before passing it to the user by USB.
But so as opposed to all the, although I'm guessing, I'm going to go out on a limb and say that I'm going to guess that the MSP430 is not a 32-bit microcontroller, but I never actually played around with them. So, but anyway, so these are full-blown 32-bit ARMs. That means you have, in one memory access, you get 32 bits back. This can also be very useful if you're trying to speed things up. So it's a better choice in general.
So we use the microcontroller for controlling the FPGA. We can reset and power cycle the FPGA because we control the enable signals to the voltage, and we also control the power of each channel buffer. So we have 8 channels.
Yeah.
That consists of 6 GPIOs, and there are buffers, and we can also just enable and disable these buffers. Also, we do provide the clock for the FPGA, so just in case you want to provide a different clock, you can easily do this with the LPC. Also, we implemented code to flash the bit stream for the FPGA.
And so fortunately, the microcontroller, as opposed to some cheaper ones, is big enough to store a full FPGA bit stream in the hex file that we distribute on these. So if you ever mess up your Datenkrake, if you use, for example, an external programmer, and you want to go back to start, you can do it. It's not a problem. You can just erase it and flash it again using the command line interface, which we'll see in a little bit. Okay, but so we also have the FPGA. In terms of us thinking about you trying to do custom things on it, we chose our pins carefully. So the other thing which can go terribly wrong if you're designing your own board is you'll basically have the worst combinations of signals ever that connect, two chips on your board. And so in this case, we spent the time, we thought about, if somebody wants to do something completely custom with this board, what will they want? And the answer is they want UART. But believe me, because UART's the easiest thing, so actually during the training, for example, everyone wrote a UART in Verilog, and I think if you ask the people who took the training, they'll attest to how easy it is to write a UART on an FPGA, and this is a perfect interface which is already there on the ARM, which on the LPCs you can clock it up to 3 megabits, and it'll do fine. So that's why we chose that. But we also have these a parallel bus, and and basically the point is, so we have the picture, I see it. I see the next slide, but it's missing. But let's go to the next slide. Next slide, please, Thorsten. So this was our dream. We want to have everyone in this room, every hacker. It's a known fact, has an Ethernet cable in their bag. So worst case scenario, you grab a pair of scissors, you cut your Ethernet cable in half, and you have a set of probes. Instead of spending lots of money on custom probes, instead of waiting for Seed Studio to send you your bus pirate probes and then getting stuck at German customs, all of these things are super annoying. So that's what we wanted to avoid. So every port has the other important thing is, so we have 56 general purpose I/O at each of these RJ45 ports that you see on the sides. So but we'll get into, so wait one second. But just the 56, we have 56 GPIO because we have 8 ports and we have 6 pins that come out over these ports. You have 6 GPIO, and you also have VCC and ground, which means if you want to design a custom board, a little board that just connects over Ethernet, you can do it, and then you can do something crazy, do your own termination, go to, well, I wouldn't do LVDS. I don't think it's the board's designed for super high speed stuff, but in general, you can design custom, basically, adapter boards. And so we'll get into that when we talk about the targets, because each one of the targets that we'll be talking about today are things that we're implementing in parallel. So we can do this 8 or more times simultaneously with this board. But so
you can think of it as an active probe that you can build. You can also just add some radio transceiver to have like 8 times in parallel doing radio sniffing.
So here we can see very quickly ARM. Above it is the FPGA. So now we should see the USB, or no, one more. Is it USB? So here's the USB. So you see the USB comes in through the bottom. We have a newer generation FTDI. It's an FT230X, which is basically, as far as I know, it's the 45 nanometer silicon that FTDI uses. So for you software guys, that means it's just newer and cheaper. Okay, and then we have these nice channels. So the channels are things that in the FPGA you can really so the question was, for example, during the training, which was, how do I interface or replace the stuff that you have there and implement something of my own? And the answer is, you replace in the FPGA. There's a logical representation for each one of these channels, and you take it and you replace it through something else, and now all of a sudden you have completely compatible to the rest of the project. You have your own custom logic function, so you can implement a CAN bus or whatever else you might want to implement, some crazy proprietary buses, SDR. I think we'll get into some of the examples in a bit. But the next thing we have here should be the buffers. So you can see we buffer the signal. So this is mainly just to make sure that make sure the FPGA isn't as tolerant as certain other things. But these buffers are definitely 5-volt tolerant, and they should work a little bit. They should work down. I would say, as far as I remember in the datasheet, it should work at like maybe 2 or so. So I haven't had that much time to try it out, but in general, the FPGA spits out 3.3 volts, but you're not going to blow it just by connecting it to 8 volts, which would be the case if you just directly connect to the I/O. So worst case, you blow one of these buffers, which are easy to replace and fix. Okay? But we also have these test pads, which are awesome. So don't ask me where I saw this first, But if you do, so I'm giving you a free pro tip. If you design a new board, what you should do is put ground planes on the corners. So now you can take your oscilloscope probe and you just take the crocodile clip and you clip it right there. And so it's not flying around all over the board and irritating you and getting in the way and grounding something out, and then you have chips exploding and whatnot. So, safety first. Okay? So yeah, and the last one's the most important part, at least for me. I want to have access to all of the signals. And on these headers, basically on the side where we have the ARM and the FPGA, you have the unterminated signals. So basically whatever the FPGA is spitting out. And on the right side, or right and left, so the outside world facing the RJ45s, you have terminated signals. So, but again, as we said before, you can disable the buffers and do something custom. You can even disable the buffers, and if you just want pure I/O on the outside world, you just plop a header down, connecting two of the pins left and right, and now you're shooting straight through without any influence from the FPGA at all. So we're thinking of people like you. Okay.
So yeah. The other important thing with such tools is to have software that is actually running on the controller, and yeah, we spent a lot of time to program some sort of a user interface. So there's a command line interface if you attach to the USB. So it's we use a FreeRTOS real-time operating system for doing all the tasks and whatever you need to implement your own task. You can just have a look in the FreeRTOS reference documentation, so you will easily get into the programming of the ARM processor. So this is how the user interface looks like at this time. So we have implemented a couple of default commands that you can use to interface to the device. So you can, this is just to illustrate.
Well, my favorite one is the write command. So if anyone here has ever, so you implement some design in an FPGA, and it's synthesized. If you did a good job, you did simulation as well. So now you want to test it. So what we did for you is if you implement something on the FPGA, you can write directly with this write command. You say address, data, and 1 second later, all of a sudden, your hardware either starts working or it doesn't. So it's, depending on if you did a good job writing the logic or not. But this is actually, this is a very important feature for if you're doing FPGA designs, because it's really annoying to figure out a way how to test if your synthesized design is actually performing as it should. Okay, so with the logic, we basically, so yeah, it's right now what we synthesized up until now is just basic bit banging, just so that people can see the things that you can, just that people can get a feel for the architecture. So if you look at the source code, you'll see that there are channel interfaces, and you can just swap these out and implement a custom channel module, and all of a sudden it won't be doing bit banging anymore, it'll be doing whatever you implemented. And internally, I hope, everything's connected through a Wishbone bus. So I don't know how well people know Wishbone, but this is actually the bus which is basically designed and supported by OpenCores. So if you go on OpenCores and you're a lazy programmer and you go on OpenCores and you steal someone else's hardware design and you expect this to work, so right before you reach that moment where you're disappointed that whatever you stole from OpenCores doesn't work because somebody did a bad job writing the code, you'll be very pleasantly surprised to see how easy it is to integrate that module onto the DDK. So at least saved you that much work. But use other people's modules at your own risk. You're actually designing hardware.
But in the end, it doesn't work at all. No.
Did you turn it off?
Try it not to. No. Okay. Yeah. Using the Wishbone bus, it's also easy to just publish your own modules, right? You can easily exchange modules that are compatible to the Wishbone bus. So.
Yeah, I mean, it's an open source bus. And actually, just to go one step further, the reason you need a bus, or the reason we've done the heavy lifting for you, is that now it's very easy for you to go ahead and have 8 modules running simultaneously, which would not be possible if you were doing an FPGA design otherwise. You would have to start writing a bus architecture. So we did the heavy lifting for you. Now you just go out and basically, grab modules from open cores, write your own modules, and integrate them. So this would look something like this. So basically, there's a bus architecture, and you write this module, you test it. It just has, it has some basic functionality. So in this case, this was what we had during our training. It's a UARTX. It would look something like this. So you put it in a wrapper that speaks to the bus, and now it speaks to the bus and is configurable over the bus, and all of a sudden you can use all of the features that we've implemented otherwise. But yeah, I mean, so now oops, go back. Okay, but now we want to talk about the fun stuff. So what can you do with hardware like this? Why would you want hardware like this? What are the things that would work better with programmable logic than elsewhere? So here's one example, which I'll leave to Olivier to explain this one tomorrow, because he'll do it more justice than I will. But for example, you can use this in chip probing, which is one of the things that I'm also working on. So in the case of chip probing, you basically you want to get signals off of the device, and using the Datenkrake, you can now, since it's programmable logic, I can now sample the data like a logic analyzer and control the chip at the same time. And if I really wanted to, I could use another port to move around whatever the microscope stage if I really wanted to. But we're not going to go in depth with that one. I think the more interesting one for people here is fuzzing embedded devices or fuzzing hardware. So this, from my point of view, is something that hasn't been looked at extensively enough. So the biggest issue here being, now I have this small, embedded device. For whatever reason it doesn't have Ethernet or whatnot. How can I interface to this easily? So now we have a platform. If it implements some custom interface, we can implement a custom interface to talk to it. And now we can connect to these devices, multiple devices at the same time, and fuzz them all at the same time. Hopefully cutting our time, dividing our time by 8. So. Yeah, I mean, the interesting thing about hardware fuzzing, you can do things like determine the state of the hardware itself. So think of an example. I mean, I'll get into a specific example in a second, but you can basically use the protocol talking to the device to see if it's crashed or not. This is possible, and you can do this completely automated in hardware without any sort of user interaction. This is completely doable. Yeah, so again, monitoring is another big thing, which is also something that I said. But you can also, if you're monitoring, you see something's crashed, you can reset it with the hardware as well. I mean, that's why it's hardware. We can toggle a pin, pull it low, or we have maybe a pass transistor, cut the power from this board, turn it off, and start it back up. And the other important thing is we can do logging, and we can do much better logging than if you were just to use an FTDI, for example, because in the FPGA you can implement much bigger buffers. So yeah, and the last one's also important. So let's say you have some serial interface to your device. Now we can multiplex the serial interface. So if you had a bunch of embedded systems, you now don't need to go around, connecting your FTDI or bus pirate to each one of these devices. You can now connect to all of them using the nice Ethernet cables, which you cut in half. And now you can connect to all these devices simultaneously and talk to all these devices simultaneously and see as they crash and restart them, et cetera. So one example that I'm working on with MeowBiz, so shout out to MeowBiz, is he asked me to help him out with the Odroid. So basically, he has this embedded device. If you look it up, it's a very small, it's almost all the heatsink that you have on these devices. I showed it to Mike Eddington. He immediately ordered several of these. He said they were cool. So basically, the Odroid the Odroid is just an embedded device that we can talk to. Runs Linux, can run Android. So we can run a fuzzer on it, and that's what MeowBiz is doing. But the issue that he has is that they crash, and there are kernel panics, which you can only see over the UART interface. So this is perfect for the Datenkrake. I can now write an interface for a device like this, write basically a UART, and it can log in the background. And whenever, I can even disconnect the PC, and so when I come back, I connect the PC and I say, what went on while I was wrong, and then you can see, kernel loops, kernel loops, kernel loops. Okay? So this could look something like this. So in reality, we just need a reset line and one TX line, so a TX and an RX to the device. So we could actually run 2 of these per channel. And this is kind of the notation that we're using in our talk, this channel X. It's to show you that we have, 8 RJ45s on these boards. So that means you can implement something like this 8 times on the board, and or do something else, or mix and match. It's all up to you. So another one that I'm going to talk about, but Olivier will also talk about it more tomorrow. So make sure to come to Olivier's talk tomorrow. Is basically hardware glitching. So hardware glitching means we somehow introduce some transient faults to the execution of the system. We play around, for example, with the voltage or the clock. Those are the 2 main types of glitching. There are crazier ones like laser glitching, which we might get to see tomorrow. But all of these things work on embedded devices. They're starting to go away on smart cards to a certain extent because they're protected against them. But if you go and let's say you have some crazy well, maybe not pay TV, but let's say a crypto coprocessor on some device, which is decrypting, some stream coming in, and you want to see if you can somehow force it to load something or dump more memory as it's loading, as it's doing a printf, etc. What you can do is you can glitch it. So glitching is, you can think of it like this, which is so the technical term is register transfer level. So you have in modern devices, in modern chips, you basically have registers, and you can think of it as everything starts in a register during a clock cycle, and it ends up in a register. So now we can either, by modifying the time, we can either play around with the period, the amount of time that the signals have to propagate from one register to the next, or we can play around with the voltage. And there we can do a couple more things. We can also affect the time, but what you see some more success with when you're doing voltage glitching is there are some high voltage, for example, read operations. So when you read from an EEPROM locally on the chip, there's something which generates a fairly high voltage to read this out, and you can basically corrupt these reads. So now all of a sudden, you have during one clock cycle, you now have some sort of nonsensical data in some of your registers, either the registers which store the opcode or the registers which store some immediate value, meaning that you now you basically can mess up the execution and make the hardware do weird things. So just to summarize, you can alter the clock period, drop the voltage, and the nice thing about the DDK is we have an FPGA where we have things like, so we have PLLs, so we can create very small parts of the FPGA which run at a much higher clock cycle. So we have a much higher resolution for doing these kinds of things. And yeah, I mean, all of this would look something like this maybe. So this is basically a module that I'm working on. So this would be how you would connect a smart card. So I maybe should have included an image of this on my breadboard, but I mean, this works. You can buy analog multiplexers. You can basically create something like a ground bounce by raising up the ground voltage. You can also drop the voltage by using a multiplexer to control the VCC of the smart card and get hilarious results.
Another use case that I mentioned before is, for example, doing software-defined radio with our device. So you can attach up to what?
Little snitch. Little snitch is blocking little snitch. Unbelievable. Recovered.
Yeah. So you can if you're doing software-defined radio. So one of my previous projects was to sniff wireless keyboards running with 2.4 gigahertz radio. And yeah, so the idea is just to add a couple of transceivers that are capable of providing a digital signal to the microcontroller. So like zeros and ones, whatever gets transmitted over the air. So we can use die Datenkrake for processing all this data, because it's really hard to do this in an ARM and write all the tools in C. So
And do it, the keyword being do it in real time.
yeah, I mean, exactly. So what you want to do is to do a real-time processing of all the data that comes over the air and match certain patterns to maybe just pass a valid packet back to the user or to the microcontroller. So the example is the Kikiriki project, which was working only with a single ARM processor, and it was pretty hard to capture all the data at 2 megabit per second, because you need to shift one bit into one register, and because we only have 32-bit registers on the ARM, you need to concatenate different registers and then shift one bit in, and then you need to compare a certain pattern, for example, the preamble, and then you need to pass the packet to some memory, because you need to store it for later analysis. So the problem is that you have, in theory, you have like 50 clock cycles with a microcontroller running at 100 megahertz, but in practice you have, minus all the overhead for interrupt routines, you have like 30 clock cycles for what can be done in an FPGA within one single clock cycle. So the example here is I analyze and I try to hack these Nordic semiconductor radios. They have a protocol and they call it enhanced shock burst. And the background is that transceiver and the receiver needs to know something like a MAC address. So the receiver will just drop any package that doesn't match the preamble and the configured MAC address. So from my point of view, I would like to sniff all the traffic without utilizing software for it. So I'm lazy. I'm also using the Nordic semiconductor chips, but I need to know the MAC address to configure to set up my own radio receiver properly. So I need to capture the MAC address basically. So and that's if you see that you don't have so much information to match a valid packet and to capture a valid MAC address, you have to deal with a lot of noise, and you need to decode all the data, and this can't be done within the ARM processor entirely. So I think no.
No, but so the main idea here being you want to do this all in real time. There are lots of very basic operations that need to happen simultaneously. You need to match bits, and in hardware, this is just a matter of generating a gate which is large enough to match the bits against a certain mask. So the FPGA can literally do all the things that an ARM can do in 50 clock cycles, basically in a single clock cycle. And it's much more efficient to implement in this fashion.
So, and this picture was taken from the USRP paper. So it basically describes how a typical SDR looks like, and if you try to implement your own software-defined radio. So you have an FPGA that is doing all the processing of the data and then passes the results to some management software that is implemented on some microcontroller, for example.
Yeah.
So this is the problem that I have been facing a couple of years ago with So this is an enhanced shock burst packet that is transmitted over the air. So we have variable length MAC addresses and variable length payloads that doesn't make it easy to capture entire packets. But yeah, we have only one preamble, which is AA or 55, depending on the MAC address that follows. So we are only interested in the MAC address. So the only thing we know about this packet is the preamble, which is AA or 55, and there are some bits in the 9-bit control header, which follows the variable length MAC address. So what we can do now with an FPGA is we can just define a huge shift register. We shift all the bits into the shift register and match the preamble, for example, and then we can also just calculate the CRC checksum at the end. So even though we don't know about the exact location of the CRC, but using FPGAs, we have definitely more possibilities to match valid packets to capture valid MAC addresses.
But basically, with the Datenkrake running at 50 megahertz, this is not a challenge at all to additionally, once you've captured one of these packets, once you've matched the preamble, to test the rest of the data, to identify this, to try the CRC out basically for any bit length, just assuming that the data you've gotten is correct, and ensure that you actually decode the valid packet. And so now you're no longer seeing noise. You see only data that's actually been decoded by the hardware, where the CRC check passed, where you match the preamble, and you don't have to. You're not second guessing yourself.
So this is a picture how the radio module could be connected to a channel. So now we can also do like so. Previously, I cycled through all the channels and sniffed the data, because you also need to know the correct channel. So now we can at least perform this task like, on 8 different channels in parallel. So that's also something that wasn't possible before. So I mean.
So now the big moment, or did you want to say something else?
I don't know.
Big moment, the release of the Datenkrake.
We told you that we are. Yeah, we already told you that we were going to release the hardware and the software, and that's done right now. I mean,
but I think there's one more step.
There's one more step. Yeah, I need to quit this.
Move it to the other screen.
Yeah. So we're going to do this right now. I don't. Does it do anything useful?
Did it work? I can't see.
Yeah. Looks good, right?
All right. So now that's only a third of it. So get ready. This part will be just as exciting. Okay, wait. No, but you're CDing into, no. FPGA, hardware, okay. So now we're pushing the board designs.
So also the hardware layout and the schematic is published right now as well.
FPGA. And now the HDL and the constraint files, everything you need to use the vendor's tools. I mean, the free. By the way, we I guess also forgot to mention it. The FPGA tools that we're using, they're not open source, but the tools are completely free. And Microsemi actually has one of the best tool chains out there, if you ask me, because they use the tools that you would use if you tomorrow start at an ASIC design shop. You would use Model Sim, Synopsys Simplify, and I mean the place and route tool is always vendor specific, but it's much more. It's the industry standard tools that you get for free from Microsemi. So I mean, if you ask me, that's awesome. So you get nice tools from them for free. So that was one of the main reasons why we chose them. And actually, Microsemi, which I guess they're also on our acknowledgement slide, but Microsemi actually, when they heard about the project, I know Richard Newell there, and Microsemi went out and they said, they want to support our project, they want to help us out, and they sent us 300 FPGAs. So for those of you who don't know, FPGAs, I mean, these are lower end FPGAs, but they still cost around $15 a piece. So that's really nice of them to go out and support our project like this. So, but I think we have a couple more people to acknowledge.
Yeah, that's right.
So I guess, yeah. So Danya, who helped us out with the layout and gave us a couple of recommendations there. Joachim Steiger, who actually did the nice plexiglass for REcon, which you'll see in a second. And Jonas, who's also a friend and colleague of mine, who helped me out when I had stupid HDL questions and made fun of me, but then gave me the answer to. And
Fefe, who's a friend of mine and pushed the project somehow by just blogging it.
So we got Fefed, which all the German people understand and no one else. And then somehow we had all these people in our IRC channel, etc. So yeah, but definitely check out the website. All that information's there. But then Hugo, Sam, and all of the other people at REcon, Eric especially, who helped us out soldering the headers for our training. Thanks to all of you guys, because there was just as much, I wouldn't say just as much work, but there was also some input from your side to make sure this works as smoothly as it did. And obviously our colleagues and Microsemi, who is, you guys should check them out. They got some bad press for no good reason last year, but they're actually a great company which is very serious about security and worth checking out. Okay, so the other thing is, you can get schooled. You can take one of our trainings if you want to get into this. We're going to be doing the workshop, but it's not quite the same as taking a 5-day training. But basically, we go over FPGA basics, some of the basics of how to do attacks as well. And so we're constantly improving on this. I mean, you can ask the people who are here, because anybody who takes our training, they're now officially a Krakenmeister. Okay, so yeah, well, there's also, so I guess we can kind of announce this to a broader audience. We're going to be doing a 3-day, not a 4-day, so not as cool as REcon by any means, a 3-day training at RExCon Breakpoint. If you're going to RExCon Breakpoint, you can check us out there. Okay, but there's also a logo contest. So, or was there one more thing? Yeah, or on demand, very important. Contact us. On-demand trainings are also available. So there's also a logo contest. So this is this one we put up here is the person here. I forgot the name. Come up here, man. Come up here. This is awesome. You know what this guy writes in the email? It says, "This logo will only win if it's the only one." I love it, man. You get one just for being a good sport. So here you go, man. Congratulations. Okay, so we're doing a couple of contests. So Hugo, we were talking about the logistics of everything. Hugo's like, we have to, so the problem was, ideally, Hugo would have liked if we made one for everyone, but in reality, manufacturing is hard, and there would have been no way to get them all done by REcon. So we made as many as we could, which was 150, so we have 150 of them here. I mean, the caveat here being, we may have done a great job presenting this, but there's still a lot of work, behind working with FPGAs. It's not like you're gonna attach it and the code's gonna write itself. You have to put some effort into it. But we're happy to teach you if you're curious about getting into this. So we're gonna be doing the workshop. So people who wanna join us there and hack on stuff there, and people who are coming in not just to get a Datenkrake will get one, because we want to see that people put some effort into it and take this project seriously. So anybody who goes over there, develops something, will get a Datenkrake. We're also doing a logo contest for people who are maybe less technically inclined, but maybe better artistically inclined. Although I personally like this one a lot. I especially like the beak on the octopus. And for those of you who didn't realize it, the arms of the octopus are actually 1s and 0s. I mean, not all of you might have caught that. And also I also like the nice touch, the N, which people keep saying there's no N in Datenkrake, but it's up there, but it's slightly down. It's not in the same, it's not in the same text box as
we saw this the first time. We thought about trolled by Meowbiz.
Yeah, this is true. We were afraid about getting trolled by Meowbiz. He's the kind of guy who would do it. But so we're going to do a couple of contests. I mean, I'll see how we announce them as we come up with them. but one of them was definitely going to be, people who now during our question session have a good feature request. I mean, feature request being something that can be done and not something, crazy. So if somebody comes up with a good feature and wants to come up to the mic and say it, we'll give you a Datenkrake as well. So we have, the point is just so that I limit myself and so that people don't try to strangle me in the hallway, we only have 4 up here. So for the other people, come into the workshop, talk to us, do the logo contest, and maybe we can come up with a couple more contests that we'll announce as the conference goes. I mean, I was a little bit upset that we had such an early talk, but Hugo thought it was a good idea. So we still have time, though. The conference is just beginning, so you'll get a chance to get a Datenkrake. But yeah, but anyway, questions, questions, comments, feature requests, logo submissions. Maybe you want to, you have very good pictorial description of what it would look like, and you convince us, and we give you one as well. No, I'm just kidding. Don't do that. Submit us one. Shoot us an email. It's on the REcon website. So questions? I mean, do we have a mic to pass around? There were no questions during Alex's talk?
It's right here.
Okay. I have to go and give it to people? Okay. There was, yep.
Does that work?
No.
Does that work now? Okay.
Yeah, good.
So, first of all, thanks for bringing us some new, nice, cheap toy.
Yeah?
Well, that's quite needing them.
I would not just call it a cheap toy. It's a very useful, low-cost piece of equipment for doing security testing of embedded devices.
I mean low cost also because, well, also, most of the low-cost tools have their limitation, like sampling speed and all. And here it seems like that you achieve to have something able to run fast enough to sample things on real-life embedded devices, which is not the case of the bus pirate, which has a limitation of 1 mega sampling speed and so on. My question also is related to sampling speed. Since obviously you use some RJ45 ports, so so are the buffers able to handle negative, so not TTL only compatible signals? Because as a physical layer of Ethernet.
Yeah, but this is so let me interrupt you with by me saying we have I think we still forgot to put up this FAQ, but the number one question we got after Fefe mentioned us was how many gigabits can I put through the Datenkrake? Yeah. And the answer is, we're just using RJ45s so that it's easy to make probes. We're using RJ45 so that if you make an adapter board, you can put an RJ45 on that board and connect it using an Ethernet cable. And for us,
you can even connect different Datenkraken together to have more
I/O. But I mean, this is what we're doing. So it's not. I mean, you could technically terminate and do some LVDS, but I think you'll have a hard time getting that to get up to Ethernet level performance. It's not going to be easy. But it's going to be hard. Actually, for those, I don't know how well you guys follow, hardware, open source hardware hacking projects, but the one to look at for that would be the Die Show, so Mike Osman's project, which we should also mention. So he's actually designing a gigabit sniffer, and he's using a much bigger FPGA. The point is, this is really lower end. I mean, our goal is maybe somebody here knows someone at Seed Studio, maybe somebody here knows somebody who can produce boards cheaply. Our goal is, we designed this hardware because we needed it ourselves. We want to make hardware which is understandable to people getting into it, and so that was our goal with this project. Our goal is not to make money. I mean, we're not making money on any of these boards. I think we might be making some money on the training though.
You actually still can generate signals. So
yeah, but
at low speeds on network devices.
No, definitely. I mean, you could try it. I just doubt that you'll get it running. Even 100 Mbit. It's gonna get really problematic. Just the signaling alone. It's an FPGA, but it's not a high-speed LVDS. Everything terminated design. Okay.
It means that the buffers need to be able to handle some negative signals and generate them. Is that possible?
No, but you can completely disable the buffers. You can bridge them. You can pretend they're not there. This is completely doable. So if you want to implement your own termination scheme, do custom I/O, LVDS using crazy, $10 chips from TI doing SerDes and then trying to read it back as fast as you can, you could try this. I mean, there's no reason it shouldn't work. It's just a matter of I mean, this is not something that the board can do as is. You would have to build some custom hardware to go with the board. But that's also for us. The point is connecting to something like an SDR or connecting something to like a smart card glitcher. It's building small modules that we can now connect to this board and run 8 of them at the same time and have all of the advantages of having an FPGA which is just doing, you know, the coordination and buffering everything and sending it out over the bus and doing all of these things. Okay, so go out there and build, you know, your custom RJ45 attached Datenkrake expansions. Erweiterungen. Okay, question over here.
So, sort of a question on hardware fuzzing. I find a device that has the source code. Right?
Yeah.
Do you have any insights on how I can marry that knowledge as I'm fuzzing the device? So if I wanted to do white box fuzzing, but on embedded devices,
yeah,
how would that work? Because I really don't know much about hardware, so I'm just curious what I can take from the
No, but
software
I mean,
side of fuzzing and apply it to these.
Well, it's up to you. Clearly, you would have to implement something on the microcontroller as well. But I mean, if there's, I can't tell you what do you mean by white box fuzzing. So you have the source code, and what are you trying to find that way? You're trying to find bugs?
Instead of generating sort of random input, right?
Yeah.
You use knowledge of the source code to do better coverage of the fuzzing.
Well, I mean, the point is maybe people got the wrong, you know, direction of what we're doing with the hardware fuzzing. With the hardware fuzzing, we're making it easy to reset the hardware and do all of the management in the background. So to send, let's say you boot something up, you know, you have to, let's say over the serial console, you have to type in root, you know, tour, whatever, to log in, and after that you want to execute, you know, some script that starts running. You could easily do this using a Datenkrake. So then you would have devices which are, you know, getting reset. They're maybe not connected via Ethernet to the network, but so you have these devices which are offline, and now you're speaking serial to all of them simultaneously. And as they crash, you reboot them and start everything over. So it's for doing it. It's the point of this project is not to do the hardware fuzzing for you. In that sense, it's interfacing, making it easy to interface to all these devices. Okay? So next, we still have 4 left, guys. Come on. I see one back there. Should we pass 2 mics? Should we? I don't know.
Hello.
Okay.
I'm wondering, is it possible to cascade the clock from one Datenkrake to other ones? And also, do you have plans for possible GPS discipline 10 megahertz or 1 PPS input?
Okay, so this was actually, that's a good question. That question alone deserves a Datenkrake, I believe. You should come up here and get it either now or after. No, but so one of the things is with I actually don't remember the answer to this question. I think we left some of the global pins for this reason. Oh, the case, man. That's the best part. It says REcon on it. It's unbelievable. So we have there are some, as far as I remember, although I don't want to be wrong on this. I think there are some global pins left. So you could do this, but I mean, the point is, so my short answer is I'm pretty sure you can do this. And my long answer is, if you come to the workshop, I'll check in the data sheets and I'll tell you an exact answer. So with FPGAs, to clock them reliably from an external source, the issue is for a lot of people who haven't done FPGA designs, you have to have specific pins exposed. So I know we have the specific pins exposed going to the ARM because the ARM clocks the FPGA and it goes straight into the PLL. I'm pretty sure we have some of the pins exposed somewhere on the board. So you could do this technically as well. Sorry, you have more questions?
Just for the next version, if people plan for that, because usually when you're doing clocks, you want to have it over coax. You may want to just
no, definitely.
put a board layout for like a MCX connector or something like that, so they can have shielded clock.
No, definitely. So this was something that we were considering doing, and we strayed away from just because it was I mean, at some point we had to start cutting features. We can't do, you know, we can't implement everything that everyone ever wanted. We try to keep it down to things that most people will need who are doing, you know, sniffing buses, interfacing to other devices, automating their fuzzing setup, etc. 3 more boards. Yes.
Hi. Neat presentation and cool hardware.
You don't get a board for complimenting us.
No worries. One question is, does this FPGA have any analog input capability?
No, actually, so this FPGA, that's also very good question. So the FPGA does not, this FPGA does not have analog input capability. So this was something that we strayed away from. This is the lowest end FPGA, but it's not the absolute lowest end, but it's a very low end FPGA, but it has the advantage of being, I think if we get someone like Seed Studio to manufacture this board, I think we could get it manufactured for get it on Seed Studio for like 60 or 70 bucks. So that was our goal, to keep it cheap so that you can buy, you know, you can have as many of them as you have bus pirates, you know, because they're not that much more expensive.
Adding an A to D wouldn't be difficult.
Yeah, it wouldn't be difficult. You could easily add it to one of the ports. It's completely expandable. So if you have a 8-bit A to D, maybe you would have to use 2 ports, or you have some way to serialize this. You have an SPI A to D. You know, all of these things are available. You could definitely still use this.
Yeah, and that's the other question. How fast can you drive the SPI bus?
So the FPGA is running at 50 megahertz currently in the current configuration. That's not using the PLL though, so you could bump the FPGA up. You could implement a SPI, which runs in its own clock domain. So then you could clock it even higher. So you could do some of these things to get really fast speeds. Right now, with the termination, the other thing which we kind of forgot to mention are the buffers are bidirectional auto sensing. So you can, on one port, you can talk output on 2 of the ports and talk input on 4 of the ports, and the buffers will detect this and it'll work fine. But the point is with something like getting back to an A to D. If you had some serial A to D, for example, you would run into issues with basically the buffers. Officially the datasheet says they can do 33 megahertz I/O. So this would be kind of a physical limitation. But if you had something that can go faster than that, you could easily again bridge the buffer and just talk pure I/O to your external device. But good question.
Well, 33 megahertz is pretty good for a simple software-defined radio.
Exactly.
So
that's what we think as well.
Nice. And then one feature suggestion or a kind of question is how many SHA hashes per second?
So this was number 2 on our FAQ. This is not a Bitcoin miner, okay?
No, but I'm just out of curiosity. What would it be?
I don't even know. So if you want to come to the workshop and implement a Bitcoin miner, I'll even give you more than 1 Datenkrake if you manage to do that.
Cool. Thanks.
We can, with 150, that would be interesting to see how many we can mine Hugo some Bitcoin. Okay. Oh, so this is getting ridiculous. We should cut it off at some point. Next we should do maybe last question. I thought Hugo would be kicking my butt. No? It's lunch already, isn't it? Yeah. So the point is, so let's do maybe last question or just last 2 or something like that. But let's cut it down, because if you guys are interested, Thorsten and I will be absolutely happy to. Okay, well, let's do two more questions just to be fair, and anyone else who wants to talk to us, who wants to see the boards, touch them, poke me and Thorsten, you can come to the workshop.
Quick toolchain question. How long does it take you to go from a blank VM to all the tools necessary to build everything off of the Datenkrake?
So could someone raise their hand? I didn't see where this was in the room, the question. Sorry, is it up where? Oh, okay. So what you could basically, well, I mean, you could comment maybe quickly on the ARM toolchain. So
Yeah, we were using the Crossworks IDE for developing and debugging all this stuff because if you want to buy a non-commercial license, it's like 140 euros, and that's maybe everybody can afford it. So also they use probably GCC on the backend. So our goal was also to provide a make file for all this stuff, so that we can also just build the binary using GNU make, for example. So nevertheless, I just recommend to use one of these IDEs because you can easily debug your software.
But eventually, we're going to release a makefile version as well, I think.
This is definitely our plan. We just do this.
But for the FPGA stuff, I mean, I don't know what to tell you. It's unfortunately, it only runs on Windows. Well, no, technically officially it runs on Red Hat Enterprise Linux 11. So as well, but I don't have Red Hat Enterprise Linux 11. So I just have, I have a Windows VM for this kind of development. You're okay. No, so we'll see you guys. What? No, so it's lunch. Yeah, let's anyone who's still interested, let's go to the workshop. So thank. Okay. They stole it. Here.
Can I just ask one thing, quick question?
Okay.
You were very impressive last year with the side channel analysis of the photonic side channel analysis. And I saw you have a new fantastic paper about cloning on physically unclonable functions. What role, if any, did this Datenkrake play?
Offline, man.